And for the conference dinner tomorrow, remember for those who went to the conference dinner last this week, the conference dinner is not included, but for those who arrived this week, the conference dinner is included in the registration fee. And those who are going to the conference dinner are Ernesto Camp, Pedro, Manuel, Diego Cogolo, Carlos Pires, and Raquel. So is there anyone else? No, I said Diego Cogolo. For the what? Oh, okay. So you're going to? Okay, awesome. Oh, you have it? So you're going to? Okay, awesome. So two more. Huh? Okay, so we have more. I'll get the names later. Now, because we are not in that large group, probably we'll go to Camarões instead of Sal e Brasa. If there is any objections, please raise your hand. No objections? Okay, as expected. So let's continue with Pedro. Thanks, Pedro, for coming.
Hello. Yeah. Okay, so thank you for the invitation. It's a pleasure to be here again in Natal. And first I have to apologize for the change of subject. For some of you may have seen that I would talk about neutrino in cosmology. But then talking with Fernando, we decided that we could change the subject to decoherence on solar neutrinos. This is related to a recent work that I'm finishing now. And so the idea is to study what solar neutrinos can tell us about decoherence. And then I'll start talking about decoherence. What is decoherence? You, on neutrino oscillations, you already saw several times this kind of formula that describe the oscillation probability from one flavor to another, in this case the survival probability, which depends on the mixing angle and on the squared mass squared difference, the distance from the production points to the detector, and the energy of the neutrino. And this formula is the simplest one because it involves only two neutrino families, but is already enough to make some discussions, because the probability, of course, is not what we measure, right? The experimental world, as usual, is much more complicated, so the probability is just one ingredient that we have to convolute with a cross-section, the flux, probably some energy resolution here, and then you have some event rate on your detector. And so to access the oscillation pattern of the probability, you have to be sure that you don't lose this oscillation pattern while doing all this integration. And in fact, it's very easy to lose this pattern. For instance, we have two effects that can wash out this oscillation pattern. It's not decoherence per se, it's an effective decoherence that you cannot detect the oscillation pattern because you don't have, for instance, enough energy resolution on your detector. For instance, for solar neutrinos, this is a main issue, you have to average over the production point. And solar neutrinos are produced in more or less 10%, 5 to 10% of the radius of the sun. So when you detect a neutrino, you don't know where this neutrino were created, so you have to do some integration on this, on this L here, because you don't know the exact value of L. And also you don't have, you have some finite energy resolution. And this energy resolution, I will put some numbers in the next slide, but it's also crucial for solar neutrinos. It's crucial for washing out the oscillation terms in the solar neutrinos. Besides those two, we have also real decoherence effects, in the sense that this really kills the oscillation. It's not that we don't have resolution enough to see the oscillation, but the oscillation is not there to be measured. This is the decoupling of mass against state wave packages. the neutrinos, as you saw several times, the neutrino, an electron neutrino is produced as an admixture of different mass eigenstates. So they propagate with different velocities. So the spread of these mass eigenstates causes a loss of coherence. So you have to take this into account, and this is not included in this kind of very simple two-family probability. And also you have the energy determination of the associated particles in the production. For instance, if you produce, let's take again solar neutrinos. You produce the solar neutrino by a decay. Let's take a boron neutrino. And then this neutrino is an admixture of two states with different energies. So it's not a problem because we know that quantum physics allow us to live with these two energies, but it also produces some other products that if you determine the energy of these products with enough precision, then you kill the oscillation pattern. This you have to take into account, and also this can wash out part of this oscillation pattern. Okay, to put some numbers, this is what happens when we put numbers on solar neutrinos. We have let's calculate the phase of the oscillation, which is the delta m squared over 4e times L times the distance, and put typical numbers for solar neutrinos. L is the distance between Earth and the Sun, the energy around MeV, and the mass square difference around the value given by us by Camelant, given for us by Camelant. And then if you cook these numbers, we have this factor here, 10 to the 7, indicating that the phase that it's inside the oscillation pattern on the probability, it's very, very large. So any small deviation here, for instance, let's take 1% uncertainty on the energy, energy resolution lower than 1%. Then this will give, this will wash out 100,000 phases of the oscillation pattern, just for 1% uncertainty on the energy. So it will be really impossible to see this pattern in solar neutrinos. So it's very safe to say that solar neutrinos are detected as fully incoherent when it arrives at the Sun. If we put here supernova, 1987, even more, because everything here is more or less the same, but we have then the distance to the supernova. So solar neutrinos are incoherent, and then we can talk about also other extra solar system neutrinos. For instance, just again to cook some numbers, if we take the ultra high energy neutrinos, energies around TeV, distance of order of kiloparsec, that would be some neutrino inside our galaxy. We know that this is not very representative for the ultra high energy neutrinos because they probably very certainly are coming from outside the galaxy, so we should have here megaparsec instead of kiloparsec, but things will, if we put this distance here, things will get even worse. So cooking these numbers, we have this 10 to the 9 factor here. So again, very safe to assume that ultra high energy neutrinos that are being detected at IceCube are arriving here in a complete decoherence state. Okay, so we cannot, there are also other ways to produce this decoherence. These mechanisms that I listed are standard mechanisms to produce decoherence. We also can produce decoherence by open quantum system formalism, assuming that, for instance, the neutrinos are interacting with some environment and exchanging information with this environment. So this environment can induce some loss of decoherence. And then how to implement this is to change the Liouville equation. This is the Liouville equation that describes the neutrino evolution. And then we can add here some terms that accounts for these interactions with some environment. And I will not go into the formalism. The formalism is quite extensive, and here is not the place to open all the numbers, but if just to put some names to the parameters that describe this decoherence, if we expand, for instance, this three neutrino families in SU. This is SU3. Sorry. In the mass, we expand this in the Gell-Mann matrices, and to make the calculations, we can transform this 3x3 system to an 8x8 system, and the decoherence parameters can be chosen to have these values, a diagonal matrix with a lot of new parameters. These parameters has some properties. For instance, the decoherence that will kill that oscillation effect are those, gamma 2,1, 3,1, and 3,2. Then enters here, 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 here. And there are two parameters that doesn't cause decoherence, but we call them relaxation parameters because the effects they have on the survival probability is a little different. It's easier to see here the effect on the probability itself. For instance, those parameters that cause decoherence kills this kind of oscillation term on survival probability. This probably, I don't remember, I think you saw this completely general expression for probability, for flavor conversion probability, and you have the oscillation terms here and here. So the decoherence parameters kills these oscillation terms here. So what you get is some flavor conversion probability, but with no oscillation effect. And so these are the parameters. And if the relaxation parameters enters differently in the survival probability. For instance, you on this specific choice, there one small comment here. There's a lot of different ways to. It's a lot of parameters, so you have to choose you have to make some choices how to implement this decoherence and relaxation to not to end with 10 new parameters on your evolution equation. So for this specific choice that was done by these people, you can have relaxation parameter here that also affects the non-oscillatory term of the probability. Here, this specific choice, they used one single parameter to kill coherence and induce relaxation, but it cannot be, it may not be like this. You can have different parameters to account for both effects. And one interesting thing is that you cannot have relaxation without decoherence. Also, this comes from analyzing some conditions on that new operator that induces decoherence and relaxation. If you impose conditions like complete positivity that assures that the probabilities are always less than 1, you don't create or annihilate particles, then you kill the possibility to have relaxation without having decoherence. Okay, so what this term here makes is it induces a transition between mass eigenstates, which is a really new effect in comparison with the decoherence effect. Decoherence effect doesn't change mass eigenstates, and so the coherence effect can be thought using a term that was used today morning. It's a adiabatic transition because it doesn't change a mass eigenstate. You don't put or take energy out of your system, so a nu 1 is always a nu 1, a nu 2 and is always a nu 2. However, when you allow this parameter to induce decoherence relaxation, some transition between mass eigenstates will occur on your evolution equation. And so, everything I told you is based on a vacuum oscillation, but since I'm going to talk about solid neutrino oscillations, we have to take all this formalism to matter. How we change these parameters in matter. And actually, what happens is that the decoherence parameter and relaxation parameter, which give two very different phenomenology on vacuum, they are kind of mixed if you go to matter. They are not intrinsically different. So if you define these parameters in vacuum and look for what are the effects of these parameters in matter, a purely decoherence parameter in vacuum can induce relaxation effects in matter, and vice versa. Because you have to diagonalize, when you go to matter, you have to diagonalize your new operator, right, with the mixing angles, and the mixing angles depends on if you are on matter or on vacuum. So usually, decoherence and relaxation convert these parameters, converting one into the other, so they bring some energy dependence and matter density dependence into the probabilities. So that's the reason why we can talk about decoherence in solar neutrinos, because actually it's more kind of choice of words than the effect. Because when we talk about decoherence in solar neutrinos, we are talking about decoherence in vacuum, that when we go to solar neutrinos, we have environments that see this parameter as a change of mass eigenstate. So also in vacuum, it looks like an adiabatic transition. In matter, it looks like a non-adiabatic transition where you induce some mass eigenstate changes. And so we have some recent work, well, not so recent discussion about not so recent work, where limits on decoherence from solar neutrinos was obtained. And how we, the headline is this: how can we achieve limits on decoherence parameters if coming from solar neutrino oscillations, if solar neutrinos arrives at Earth completely incoherent already? You already killed any hope to see oscillation pattern in solar neutrinos. So they are already decoherent. So any new effects that you put on that enhance decoherence on solar neutrinos, we shouldn't care about them because they are already completely incoherent. However, when we talk about this kind of decoherence, it's not exactly decoherence on that sense that I presented earlier. It's more like a relaxation effect induced by decoherence. So if this group made some analysis and they found some limits on the decoherence parameters. Here you can see that it's purely decoherence parameter, and they arrive at these limits from using solar neutrino data, but again, because we know we are not talking about killing the decoherence effect on survival probability, but inducing some change between mass eigenstates. Okay, so based on that discussion, the idea of this recent work is to study the relaxation limits from solar neutrinos, and with a strong emphasis on the conversion between mass eigenstates. So, this, as I told you, is the same open quantum system formalism that gives that provides enhancement of decoherence, naturally provides some relaxation effect, some transition between mass eigenstates. So in principle, you can use solar neutrino data to constrain these effects, because solar neutrino data is sensible to the amount of mass eigenstates that are arriving at the Earth. And so we are setting the limits on these parameters. This, in a perfect world, I would already have put some numbers here, but it's almost there, so I still don't have a number. Maybe if Thursday rains, then we cannot go to the beach, then I'll put it. Right. Okay, so let's talk about solar neutrinos, and then I don't have to spend a lot of time because we already saw some nice discussion about solar neutrinos phenomenology by Esteban. But just since I prepared the slides, I will go very fast over them. This is the 2x2 two neutrinos formalism on solar neutrino. This is a Hamiltonian 2x2 Hamiltonian that describes solar neutrino evolution. You have the standard here, the vacuum mass and mixing, and the matter potential. And sorry, there's a minus here. That's wrong. And you have two different kinds of transitions, possible transitions. One, for low energy neutrinos, these terms, for low energy neutrinos, this term here is much higher than the matter potential term. Then the mixing angle in matter is basically the mixing angle in vacuum. But for higher energy neutrino, this term gets lower than the matter potential, then you have maximal mixing. And when you go to the probability, you already saw this, you are with energies around few MeV, you go through the transition from non-resonant evolution to resonant evolution. These neutrinos, for energies higher than 10 MeV, they are created as a fully mixtured neutrino inside the sun. And these neutrinos here for energies below 1 MeV, they are created as in vacuum. They don't feel the matter potential. Here there are a lot of different effects. For instance, you can have regeneration effects that will be quite important for our discussion. For higher energies, well, actually, the solar neutrinos ends here in 20 MeV, in 16 MeV actually. But for this kind of energy, you start to feel some Earth regeneration effects. That sentence is very nice. The sun looks brighter at night for solar neutrinos because during the night you can part of the neutrinos that were electron neutrinos that were converted into non-electron neutrino, they regenerate to electron neutrinos, and the sign enhance for this during the night. You have some effect on of theta 1,3. You have some the transition between resonant and non-resonant regime. And the nice thing about solar neutrinos is that for some coincidence, for the lucky coincidence, this transition here happens right inside the spectrum, solar neutrino spectrum. There's no good reason for this to happen, but we were lucky enough to have a star where with densities such that we can see this transition with solar neutrinos. And then the data, again, already discussed in previous presentations. We have Super Kamiokande data that saw 45% suppression of 45% of the compared to the unoscillated prediction. You have SNO with a Nobel Prize, 2015 Nobel Prize, and where you have an independent measurement of the electronic neutrino flux and the non-electronic neutrino flux arriving at the detector, and both added sum up to account for the full neutrino flux, which is in accordance with the standard solar model prediction. And we have Borexino with this very nice plot where you have independent measurements of different sources of solar neutrino coming from different reactions inside the sun. And also Galaxy, GNO, SAGE, Homestake. Homestake, actually, one of these days I found out, maybe I'm wrong, but I found out that Homestake is not the official name of this experiment. Actually, I don't know what is the official name, because on the papers, they don't have a name. Sometimes they call it chlorine neutrino experiment. Sometimes they call this experiment of Davis and company. So it's just because I found it recently, I put it here. And then we can translate all this information, in particular this one here, where we have the survival probabilities for different neutrinos coming from the sun into some numbers. So doing some calculations with the solar neutrino data, which are a lot of data, we can have different probabilities for different energy regimes of the sun. For instance, high energy neutrinos, which are the one detected by Super Kamiokande and SNO, we have 32% of conversion of survival probability, sorry. For the monochromatic intermediate neutrino energies, of beryllium and PEP, we have something around 50% conversion. And for the low energy, using data from Galaxy, SAGE, and recently Borexino, we can set this number to 57%. So we have basically 3 different regimes on the solar neutrino conversion. And since they are arriving here incoherently, we can write this solar neutrino survival probability as a compound probability involving the amount of Ni1 that's arriving at the sun times the probability that this Nu1 will be measured as electron neutrino, and the same for Nu2 and Nu3. Events during the day, or if we disregard regeneration effect, these numbers here are the mixing angles, basically the mixing angles of the mixing, relating the first family on the mixing matrix. So involves theta 1,3, theta 1,2, and with these numbers, cosines and sines. So we can just put these numbers here, and we can associate the survival probability with probabilities of neutrinos coming out of arriving at the Earth as Ni1, Ni2, and Ni3, which are the real particles, right? The particle, the neutrino as a particle is the neutrino with a specific mass. So the particles are Ni1, Ni2, Ni3, and electron, muon, and tau neutrinos is a combination of the real particles that interact with matter. Okay, so these are the events during the day, but during the night, things are more complicated because then you have regeneration effects. And regeneration effect, it's a non-adiabatic process. If it were an adiabatic process, it will not change anything about this probability. But since it's non-adiabatic, when the neutrinos come inside the sun, they feel a step function on density. This induces non-adiabatic transition, and then, oh, sorry, spoiler. It induces then a transition between mass eigenstates. So because for those neutrinos arriving during the night, you have to take into account some transitions between these three terms on probability. Taking all this into account, we can do analysis, purely data analysis. I'm not assuming anything about what's happening inside the sun. I'm just translating the data on survival neutrino probability to how much of Ni1, Ni2, Ni3 we can conclude that are present on solar neutrinos. And then, for instance, let's take high energy neutrinos, which are the high energy neutrinos without regeneration, which is the simplest case, because it's close to 1/3. So if a probability that's close to 1/3, in principle, we can have equipartition between Ni1, Ni2, and Ni3. By the way, these are those triangle plots, which are very nice, that IceCube is using a lot, but they are using mostly with flavor neutrinos instead of mass eigenstate neutrinos. But it's the same idea. From this plot, you can read how much of Ni1 we have, how much of Ni2, and how much of Ni3 we have on some flux, neutrino flux. So 1/3 probability means that we can have, for instance, 1/3 of an equipartition of the three mass eigenbases. But we can have also a lot of other choices of equipartition, and who decides which choices are those are the results of Super Kamiokande and informations about Diabay that fixes the mixing angle, and Kamland that fixes the Diabay, and Double Show that fixes, and Reno that fixes theta 1,3, and Kamland that fixes theta 1,2. Not very well, because you have still, for instance, for theta 1,2, you have a lot of allowed region for the mixing angle. But anyway, you can combine this information of Diabay, Double Shoe, Reno, and Kamland to find out the allowed contributions of Ni1, Ni2, Ni3 on the solar neutrino flux. So for high energy, without regeneration, we have this kind of thing. But when you include regeneration, you can start to induce a transition between mass eigenstates. And for instance, if we have equipartition, you don't have any regeneration effects when you go through the Earth, because it's the equipartitions creates a situation where if you change some amount of Ni2 to Ni1, you change the same amount of Ni1 to Ni2. then you end up with the same amount of neutrinos, and so you would not see any regeneration effects. And Super Kamiokande and SNO are seeing a positive signal of regeneration effect. So you exclude this equipartition because of regeneration effect. And low energy, the low energy, you have a different allowed region on these probabilities. This is artificially chosen to limit the mixing angle, 1-2 mixing angle, lower than 45 degrees, because we know that large mixing angle is there, right? We are not assuming anything about large mixing angle solution to solar neutrino problem, but we can fix it just arbitrarily. But we can also do the analysis on the dark side of the Cumberland allowed region, and you get similar results. And then what we can do now is include any new effect. Remembering we didn't say anything about large mixing angle solar neutrino mechanism. So what we can do is, if we induce new relaxation effects that come from these parameters here on the neutrino evolution, we can try to limit these guys, because it will take, for instance, if you come here, it will take an allowed point on this region and put it here on the outside this allowed point, and then you exclude these values for these relaxation parameters. These are the expressions for the probabilities, the conversion probabilities between mass eigenstates. And the allowed regions that we get, again, with no information about flavor conversion inside the sun, are those. There are some numbers here that doesn't make sense without comparing with another numbers. But anyway, we have limits around 10 to minus 17 GeV here. I think this is wrong. I think it's EeV. Sorry, the G is too much here. And then this is the final result that we get with no assumption on, again, what's happening inside the sun. This is purely from the data we get from Earth. And now we can compare this with the analysis that we make with full knowledge of what's happening inside the sun. We know that with this with the mass and mixing given by Cumberland, some resonance conversion is happening inside the sun, so we can take all this information into account. And supposedly we could get much better limits, but the fact is that we improve our limits, but not too much. Meaning that knowing what's happening inside the sun doesn't help much in order to put constraints on these parameters. So the conclusions is that we get these limits on decoherence parameters, and with the full analysis using all the information we have. But if we make no assumption on neutrino physics inside the sun, the limits we get are not very different. It's a factor of 2, depending here what we choose to compare. This is 1 and 3 sigma limits. So the hint here is that maybe if we take this analysis to astrophysical sources, maybe some beyond standard model of physics does not require to fully understand what's happening on the astrophysics objects to limit this new mechanism in neutrino physics. That's it. 20 seconds.
Questions? No questions?